Hi everyone. In today's video, we will be discussing about recurrent neural networks, and to understand it in a better way, we will try to explore a basic understanding of RNNs using a small numerical example. Let us suppose we are in a scenario where we need to predict the sales of a particular firm based on some financial parameters. All the five financial parameters could be liquidity, profitability, leverage, valuation, and solvency. We need to find the sales corresponding to a weekly basis, and we have a data which might look like this. So this could be the five financial parameters spread across the 5 weeks we want to know. These are all made up parameters or made up values. This is not actually related to a particular firm. So this could be liquidity, this could be profitability, leverage, valuation, solvency, and this is the value of liquidity in week one, in week 2, 3, 4, and 5, and so on. So we have the data corresponding to the five parameters in the 5 weeks. Now we need to find the sales, which is itself a regression problem. And now we see two things over here. First of all, there is a time dependency present where sales of 1 week depend on the previous one, and the features may be dependent on each other in more than one ways. We can use the traditional machine learning methods, where one uses a forecasting technique where a simple boosting regressor is fed on the data and the predictions are made. However, we won't be able to get the interdependence captured between the features in more than one ways. For that, we use a method where we consider a finite size matrix U, which is of order m cross n, where m is the number of hidden units, and in typical terms, it is the number of ways in which we need to capture the interdependence between the features, and n is the number of features in the input vector. The value of m could be selected based on judgment. Like I selected 6 over here, and I want to understand that in how many ways, or in 6 different ways, the features are related to each other. So u will be of order 6 cross 5. Now we pick any one value x1, which is the value of all the parameters in the first week, and it is of order 5 cross 1. So this is because if I just look into the matrix X over here, this x1 is literally, it is x1 transpose first of all, so it will be just the first row which we are going to pick up, and we are just going to transpose it. Then it will be a vector of order 5 cross 1. Now we proceed further. So this is how the U matrix is looking like, x1 is looking like, and we multiply the U matrix with x, and we add a bias term to it. Now let's carefully see how the multiplication is done. This is the usual matrix multiplication we are doing. So over here we see that if we just focus on this equation, this is a parameter which is unknown, this is again a parameter unknown, so as this, so as this, and this. Now this entire first row resembles a linear regression equation. Like b1 could be the intercept, and the other ones could be the slope. u1, u12, u13, u14, and u15 are slope, and all these terms are unknown. So just imagine we are fitting about like 6 regression models all at one go, with each regression model capturing different context based on where we start. Now we usually think that the regression will give us or a linear regression will give a unique value. But over here, since we are capturing across 6 different contexts, so definitely the value won't be unique. We will be getting different values corresponding to each of the UIs, because whenever we are fitting something like an RNN, we are obviously assuming the problem is complex enough not to be solvable with the linear methods. We are obviously trying to solve a problem which is pretty complex. Now we proceed further, and we get a vector of shape 6 cross 1. So the entire term, this term entirely, if I focus on that, this becomes u6 over here, the term above this one becomes u5 over here, and so on. We proceed further to apply an activation function on top of the results obtained, and we get something like this. So f is an activation function. F could be like sigmoid, f could be ReLU, f could be tan hyperbolic, anything. So after multiplying the matrix U with any of the values like x1, x2, and so on, I preferred x1 over here, and adding a bias term to it, and then applying an activation function, we get a term like this. So usually in the RNN terminology, S1 is called as a hidden state. So this is called as a hidden state, or in other words, the features learned by the model which could be transferred to the other state. So we will come to this transferring from one state to the other state in a bit, but as of now, just uh, assume that this u, x1 and b have been calculated, and this has been stored in a state corresponding to x1. So for corresponding to x1, which is the first value of the week, there is a corresponding s1 where the activation function is applied when multiplied x1 with u and bias added and stored in s1. We need to map the result of the activation function we have attained till now to our eventual target for 5 weeks, which looks like this. So maybe this is the sales target in week 1, week 2, 3, 4, and 5, and the one which we just calculated for S1. We have to map this S1 to Y1 is equal to 100. So, and if you see the dimension, so Y is of 5 cross 1, and the S1 which we have attained over here is a matrix of a vector of shape 6 cross 1. Over here, a matrix comes handy, which we call it as a matrix V, which is of order P cross M. So P is ideally the output features of Y1, and this is what we are going to do. We will multiply the matrix V with S1. And to make it happen, first of all, we need to make the number of rows in P to be equal to the output features of Y1. Like if I have 5 features over here, P will be equal to 5. If I have 100 features over here, P will be equal to 100. If I have 10 features over here, P will be equal to 10. So if y1 is a vector, as of now, the number of output features of y1 is just equal to 1 only. But if the output features were like this, 100, 200, and so on, like we are trying to predict a stream over here of values, then we just need to take the dimensionality of it and put the value of that in P. So as of now, the output features of y1 is just one, like there is only one value 100 which we are trying to predict, and M is the number of hidden units which we established previously, which was equal to 6. On doing so, we get the vector V of shape 1 cross 6. So this is how we are placing the vector V. Now we multiply with S1 and add a bias term C to it, which will look like this. We knew that the term which we got previously was fu1, fu2, and so on till fu6. This was a vector, that's s1 only. S1 consisted of these fi's, and then when I multiply the vector v with s1 and add a bias term c to it, this is what we are getting over here. And since again we are in a deep learning domain, we will apply an activation function on top of it, and eventually we get the predicted value as y1 cap. So this is the predicted value, actual value is y1, and then we proceed further to the next iteration and so on. So this is what has happened till now. So we started with the initial set of matrix, which was this X. It was a matrix of order 5 cross 5, 5 being the number of rows and 5 being the number of columns. Like we observed the matrix X for 5 weeks for 5 variables, and then we had to predict one target variable, which was the sales, and then we wanted to know the relationship amongst different features in the model, and we wanted the model to learn it because we assumed the model is not linear enough to learn only one set of features, but we have to learn multiple features out of it. Then we set up the number of hidden units as m, which we set as 6 over here. Then we established a matrix u, and we multiplied it with x, or we took just one value x1 corresponding to any particular week. We multiplied it, we got u into x1 plus b, and this kind of resemble the form of a linear regression which we have studied previously, and then we applied an activation function on top of it to get the hidden state. So this is how a particular, so S1 is exactly in layman terms the summary of xt at time t. So st is the summary of xt at time t. Now we need to use that summary to generate the features, or in other words, we need to understand the summary, which is exactly the learned dependence between the features to predict the actual results. We then look into the prediction data, which looks like this. We need to fit a model which will be predicting terms like these 100, 120, 150, 140, and so on. We pick up y1 because apparently we picked up x1 in the previous step, and then we design a matrix V which should be of order P cross M. P is ideally the number of output features of Y1, which was just one only over here, and the number of hidden units was 6, and then we multiply it. And this is ideally, if you see why we are doing it, in previous step we got a vector of order 6 cross 1. Now we need to reduce it to 100. Like all the understanding we got in the hidden status one, we need to map it to 100. So in order to do that, we needed another matrix over here, which was V. We do the usual matrix multiplication with the bias term added, and then we get the final predicted result as this. The activation function is definitely needed because the predictions may be in real terms. In order to map values which may be very small to real terms, an activation will be needed for sure. So that was the main reason the activation G was needed over here, and likewise the activation F was needed in the previous step. Now to summarize in a diagrammatic way, this is what has happened. So corresponding to x1, which was our input vector, there is a u which is mapping to s1, there is a v which is mapping to y1 cap. Now corresponding to x2, there is that u again which is mapping to s2, there is a v which is mapping to y2 hat, and so on. Now all these parameters u and v, b and c are the hyperparameters which needs to be learned by the model, and how it will learn it. So first of all, you will be initialized randomly to a particular value. Like in our case it was a 6 cross 5 matrix, so it will be randomly initialized to any of the 6 cross 5 matrices, and there are various ways to initialize a particular matrix in TensorFlow, Torch, and so on, one of them being Glorot uniform. So I just pointed out one way, but there are other ways to initialize as well. But the initialization will happen, and then one forward pass will go, which will take x1 to s1 and then s1 to y1 hat. And then on observing the deviations between y1 and y1 hat, which is ideally, you can say, the root mean squared error only, and we will observe it for the entire batch. Let's say I selected a batch of k observations. We then do a backward propagation where we apply the gradient based method to update the weights u, v, b and c. Now if I have to write everything formally, this is how it is going to look like. First of all, we have xt, we multiply with u, and we add a bias term. We then apply an activation function on top of it to get st. Now use that st to obtain yt. So first learn the features and then use the learned features to map it to the target. So these are the parameters which we need to tune over here. Now if I see the diagram which I draw above properly, we can see that all the hidden states like s1, s2 till st are all independent. Like it is calculated over here, and prediction comes in. The s2 is calculated and the prediction is done. But what if we need to establish a connection between the previous hidden states? That can also be done, and if we do that, we get an architecture which looks like this. So from xt minus 1, st minus 1 will be calculated with the weight u and v. The only difference is the information from previous step is calculated, or the information from previous step is propagated to the current step using a weight vector w, and consequently we can enhance the learning by considering the dot product of u with xt, which we had been doing previously. The bias term was there previously as well. We just incorporate one more term, which is multiplying the weight matrix with the states or the information from the previous term. We don't need to take the previous input, because because as I have told previously, the previous input was taken and it was properly summarized over here. Just to speak in layman terms, we just take that summary of the learned features and pass it on to the current step. So this becomes your extra additional feature, which will help us in understanding the interdependence between different features at different points of time across different steps. And the calculation of yt goes on as usual, so there is nothing which changes over here. The only change goes in the learning of the hidden state. St in many places could be written in the form of ht as well. Both mean the same thing and are used interchangeably in literature. So as soon as I introduce the term w over here, we get the parameters u, v, w, b, and c. So we just got one extra parameter to tune in the backward pass of the model, and this is that parameter which we will be tuning. Now, after having done an initial understanding of how an RNN looks like, let's try to solve one of the problems which I have found from Chet. I will link the problem in the description and you can have a look over there as well as to what this problem is. So over here we have the hidden state equation, which is exactly what we were talking previously, just that s is replaced by h over here. So in our case it was st is equal to w times st minus 1 plus some u times xt plus b bias was there, and on the top of it we were applying an activation function. So over here this term is not present, u is not present, so it's just xt over here, and the bias term is not present. We just have w times st plus xt, and this is just a linear activation function. So that's what this equation means over here. And the input vector at time 0 is this, and the consequent input vectors are this much only. Like in previous case, we had an input vector of size 1 cross 5. We are having an input vector of size 1 cross 2 over here. And the initial hidden state is just null vector, and then we have the weight matrix initialized somewhere. So maybe they started with this initialization. Usually this will get updated over the period of time. Now they want to understand that whether the hidden state is going to settle down to a particular vector or not. Now if I look carefully, uh, this equation which they have given over here in the question, this seems like a recurrence equation to me, with a proper initialization done at h minus 1, which is over here. Now we need to get the recurrence equation solved to a particular form. Now if we proceed from the first principles, we have something like this. So we have this recurrence equation. We put the value of x0 as 10, which was given, h minus 1 as this, and we calculate h naught. And on doing so, since h minus 1 was actually a null vector, this entire term gets cancelled, and what we are left with is x naught. Now we proceed further in the calculation of h1. We are able to calculate wh naught plus x1, and again x1 over here is 0 0 as mentioned in the question. So we are just left with w times h naught, and h naught could be replaced by this substitution, like we replace h naught with x naught. Now we proceed further to find out that h2 is w square h naught, and consequently we can generalize that hn is w raised to n x naught for all n greater than equal to 1. Now we need to find the limiting value of Hn. Just remember that Hn is W times n x naught. This we need to remember. Now, in order to do that, we have to do this, and we have the term W, which could be decomposed into PDP inverse using the diagonalizability theorem of eigenvalues. We can say that if W is a matrix, and it's not even a big matrix, it's just a 2 cross 2 matrix, it could be, yeah, this is W, 2 cross 2 matrix. Now we can easily decompose it into PDP inverse, where D is the matrix of eigenvalues in the diagonal elements, and D is a diagonal matrix only, and P is the matrix of eigenvectors corresponding to the eigenvalues. Now, if such a representation is there, and this is actually a principle of diagonalizability in the eigenvectors, so W raised to n could be represented in this form. So instead of taking W and multiplying it n times, we can just reduce it into a diagonalizable form and then take the power of it, and just we need to make sure where d raised to n converges to, or we just need to calculate d raised to n, which is having much less computation involved than multiplying the matrix over and over again. So in order to calculate D, which is ideally the matrix with eigenvalues as diagonal elements, we proceed with the characteristic equation calculation. First, we form the characteristic equation. It's a 2 cross 2 matrix. By Cayley-Hamilton theorem, it's lambda square minus the trace of M, or I should say W over here, and the determinant of W. On doing so, we get the two eigenvalues as zero point 0.5 and 1. You can actually calculate it using the W minus lambda I determinant equal to 0 as well. I just use this to save time. So I get these two as eigenvalues, and consequently our matrix D looks like this. So the first eigenvalue placed over here, second eigenvalue placed over here, and the rest, because it's a diagonal matrix, the rest of them being 0. Now let's power d raised to n to n. So we get 0.5 raised to n, 0, 0, 1 raised to n. Now if I even do 1 raised to 100, anything, it will remain as 1. But if it is 0.5, let's see the trend, how it's converging to 0.5 square, it will be 0.025 or 0.25, I should say. And if I say 0.5 cube, it is 0.125. It's decreasing slowly and gradually. At one point of time, 0.5 raised to n, it will kind of tend to 0. So that's what we use over here. We say that as soon as limit n tends to infinity for dn, the term 0.5 raised to n is 0. The diagonal elements are, non-diagonal elements are 0 anyways, and this term, which is 1, is at 1. So this reduced a lot of our calculations, and if we revert back to the step that W raised to n will involve P, D raised to n, P inverse, and the limiting needs to be done, we are just left with the calculation corresponding to P and P inverse. So we proceed further for and P is actually the matrix of eigenvalues, matrix of eigenvectors. So we consider the first eigenvalue 1, and then we proceed further with calculating the eigenvector, which comes out to be 1. I'm not going into the details of how to calculate it because I assume it will be quite intuitive by now. And for the second eigenvalue, I get the eigenvector as this 1 comma minus 1. So on clubbing these together, we get the matrix as this, the P matrix as this. We need to normalize it as well, because actually P is a very normalized matrix, and the reason why we normalize it is the fact that it is like orthogonal. This is also one reason. So now we proceed further, and then we say that W raised to n is P, D raised to n, P inverse. We do the multiplication, and then we do the limit of it, and then conclude that limit n tends to infinity Wn is this matrix where every value is corresponding to half, 0.5. Now let's review the initial task which we had to do. So we needed to find the value of n tends to infinity W raised to n x naught, because we need to find the limiting distribution of Hn. So we are over here that Hn is equal to W raised to n x naught. We limit it with n tending to infinity. This is a constant, it won't be getting affected. We need to find the value of limit n tends to infinity W raised to n, which we just found over here. We just substitute it and we get the limiting distribution of Hn as half and half. So it will converge to two values which are equal. So that was it from this question. which was more of a recurrence question than recurrence neural network question, where we were trying to find out the limiting state corresponding to the hidden state whose equation was given by this. The equation was pretty much similar to the ones which we kind of intuitively derived in the previous step, and with some set of initial conditions we were able to get the results corresponding to it. So that's it for this video. In the next video, we will be solving another important problem using RNN, which is commonly called as a parity bit problem. Thanks for your time.